All right, so today what we are doing is a very important topic. This is something that is essential. Remember, first semester doing chain rule. Chain rule happened all the time. Even when we weren't in the chain rule lesson, every time we did a problem, we had to do chain rule. Okay, it was something that happens pretty much, I'd say 70% of the time you take a derivative, you probably have some sort of chain rule involved. Today we are doing the exact opposite of chain rule. Okay, it is integration with a chain rule-esque problem. It is going to be called U substitution. If you broke this chapter in half of it would be U substitution, half of it would be the things that we've done, the FTC part, okay, the fundamental theorem of calculus. So this is really important. I'm going to spend many, many days doing this. All right, so this is not a one day, oh, that was weird and tough, and so now I'm going to quit. It's something you have to keep getting better at. It's as essential as chain rule. I would say that this is probably one of the toughest topics we teach just because there's a lot of steps. But if you follow the steps, it's also very systematic as well. Okay, if you're good at step following, these problems are easy. If you get lost in the sauce, then you might have to adjust a little bit here. Okay, keep focused on what you're doing. Number one, we are taking the derivative 2 sine of x over 2. Yes, sir. All right, I'll bring you one. 2 sine of x over 2. We're taking the derivative of that. What do we need to do to take the derivative of 2 sine x over 2? What rule are we using? Chain rule. Katie, talk me through. What'd you do? Yep, derivative of sine is cosine. Rewrite the baby, x over 2. What's the derivative? 1/2. The 2 in the front was a constant. Nothing happened to that 2 in the front. And then she multiplied by the derivative of x over 2. It got you 1/2. What happens with that 2 and that 1/2? They cancel, leaving you with just cosine x over 2. That's my answer. Same thing with the next one. -2 natural log of 5 minus x. We are taking the derivative of that thing. So, Nick, if I want to take the derivative, what can you do? Yep. It's the derivative of natural log is 1 over. And so the -2 is a constant. And then it's 1 over the baby. So what's the baby going to be? Yep. And then what else do you got to do? What's the derivative of the baby here? -1. The derivative of 5 minus x is just -1. And so -2 times -1 is just going to be 2 all over 5 minus x. Today what we are doing is we are going to integrate that thing. We have to go back a step. It looks kind of complicated. We'll try to figure it out today. That's going to be the main goal. All right, so today we are starting off here again with indefinite integrals. We are doing integrals here without bounds, indefinite integrals. So remember when it's not bounds, when we take the antiderivative of f of x dx, that's capital F of x. Don't forget the plus c. You have some constant at the end. We've talked about that before. But when we take antiderivative without bounds. Right here, there are some indefinite integral formulas. These are shortcuts of what we're going to do today. If you get good at these shortcuts make a lot of sense, and you can go in about a quarter of the time that I'm about to show you. I am showing you the long way first. The reason I'm doing that is because the process that we're going to do is a little bit weird. If you do it with these easy ones, then it'll make more sense later on. There's a faster way of doing this problem, but we're going to do it the long way first and then adjust. So when we look at letter A, hopefully you see some characteristics of a chain rule problem. You've got cosine, you've got x over 2 inside the parentheses. There's a baby in there. All right, so what we are going to do here is we are integrating that. We're going the opposite way. The opposite of chain rule is U substitution. So the antiderivative cosine is sine, but that x over 2 really throws everything off. So what we're going to do first is we're going to set the baby equal to u. So u is going to be equal to x over 2. U is just a replacement. It makes it easier on your brain. All right, there's nothing fancy about it. It is just a space holder. Okay, it's basically like you're covering it up and you're saying something's there. I don't know what's there. Let's just call it u for right now. That way we don't have to mess with the ugliness of it. That's all u means for us here. So u for us is going to be whatever's inside the parentheses. It's x over 2. Then over here on the side, we are going to take the derivative of u. And you need to write it like this because it'll make more sense. The derivative of u. So du over dx. What is the derivative of x over 2 going to be? 1/2. One other thing I'm going to do here is I'm going to then solve for dx, because here in a second I'm going to do a substitution problem. So I want to get dx by itself. Right now it's not by itself. It's on the bottom. So I'm going to multiply both sides by dx. Is dx by itself now? No, it's got that 1/2 with it. How could I get rid of that 1/2 on the dx side? Multiply both sides by 2. And so 2 du is equal to dx. So what we just did is we set up some substitution stuff. Based on those concepts over there, we are going to substitute what we got into this problem. So my problem is now going to look like this. I'm still integrating. I haven't done the integration yet. That's the one thing you'll skip, is you'll do all this side work and you'll skip the fact that you integrated. Cosine. Instead of writing that ugliness there, we're just going to write u. And instead of dx, we are going to write what dx is. Dx is 2 du. Do you have a constant in that integral? Yeah. Anytime we have a constant in the integrals, pull it out in front because it just makes this problem easier. So now I've got the problem 2, and I'm going to integrate cosine of u du. It's not a complicated problem anymore. Now it's just the integration of cosine. What comes before cosine? What's the antiderivative of cosine? Sine u. I integrated without bounds, so what else do I need when I take the antiderivative? Plus c. When I integrate du, that's the plus c part of it. That's the constant. And so that du does become the plus c. And then the only thing I have left is plug back in what u was. We set up here at the beginning, u was equal to x over 2. So cool, let's rewrite it in terms of what we started with, which was x over 2. So 2 sine x over 2 plus c. That is the answer to this guy. A little bit funky to get to that point. I understand a little bit of the, that's weird. Just trust it for right now. All right? This looks kind of strange. That's the antiderivative. If you don't believe what we just did, take the derivative of that guy. What is the derivative of 2 sine x over 2? It'd be 2. What's the derivative of sine? Cosine. Rewrite the baby times the derivative of the baby. What's the derivative of x over 2? And the derivative of some constant goes away. The 2 and the 1/2 cancel. That's what I started with right there. That is the antiderivative.
And we don't have to put the squiggly in our answer?
What squiggly? This is my answer. No, because we took the antiderivative. The antiderivative, we did that aspect of it. That'd be like saying 3. It's like saying the square root of 9. Well, the square root of 9 is 3. I don't put the square root sign anymore. I took the antiderivative. That was this step right here. By going from cosine to sine, I took the antiderivative.
Does that have a name?
I think it's a squiggly. It's the integral. Yeah. But we can call it the squiggly. It makes more sense. Letter B. Let's try it again. All right? It's a little bit funky. We've got to get used to it. Right now, we're doing this for like 2 weeks. So don't be scared just because the first one was weird. We're integrating 3 over x plus 2. I would always suggest in these problems pulling out a constant if you have one. Do you have a constant in this one?
3.
I got this 3. I'm going to pull it out in front. So I'm just going to rewrite this problem as 3 integral of 1 over x plus 2 dx. Although it might not look like it, this is a chain rule-esque problem. Because in the bottom of that denominator, all of that is together. That x plus 2 is all together. You can't just write it as x to the negative 1 plus 2 to the negative 1. That's not the same thing. So the first thing we're going to do when we recognize, hey, this is a u substitution problem, u is going to be equal to the denominator in this case. So u is equal to x plus 2. I'm going to take the derivative of x plus 2, du dx. Show me with your fingers what's the derivative of x plus 2. Derivative of x plus 2 is just 1. I'm going to solve for dx. So I'm going to multiply both sides by dx. That one was easy. Du is now by its, or dx is now by itself. Du equals dx. It's the easiest substitution of all time. Now that we have figured out what u is and what du is, we're going to substitute in for those two things. So my problem is now going to look like this. 3 integration. I haven't done the integral yet. 1 over. What's going to go on bottom? U. I'm plugging in for x plus 2. And instead of dx, I can just plug in du. Okay? We're going to take the antiderivative. What is the antiderivative of 1 over u? What, when you take the derivative of it, gets you 1 over u? ln. Natural log. And remember, when we create our natural log through antiderivatives, we do put it in absolute value signs. That was something different. So it's ln of u in absolute value. Plus c. I took the antiderivative without bounds. It's plus c. That's not my answer yet. My final answer is that guy with my u plugged back in. Absolute value of x plus 2. It's because we can't take the natural log of a negative number. And so because of putting those absolute values, it gets rid of that possibility. Questions with that? It's weird. You'll get better. Look up above. There are formulas for this. This is a formula that you could pick up on pretty quickly if you were good at this. This is what we just did. 3 over x plus 2. The antiderivative of that is natural log x plus 2 plus c. Yeah, that's what we just did. If you want to go through and memorize those formulas, great, use them. But the antiderivatives work as well, using u sub. Looking at letter C, let's try one more together here, or at least I'll get you started. There's a constant. Pull the 2 out in front. That is a u substitution problem because you got that weird stuff in your denominator, 5 minus x. What do you think your u is going to be for this guy? 5 minus x. Take the antiderivative. Do that now with your neighbor. So let's check this thing. Again, you were pretty good. Just the negative sign threw us off. The derivative of 5 minus x. Show me with your fingers. What's the derivative of 5 minus x? That's negative 1. I need to get dx by itself. So technically, I'm going to multiply both sides by dx. But then I would want to divide by negative 1. So dx is going to be equal to negative du. Negative, and if you want to make it negative 1 du, that might make a little bit more sense to you. So I still haven't done the antiderivative. I'm plugging in 1 over u because I'm plugging in my u. And instead of dx, I'm plugging in this guy times negative 1 du. Do I have any constants when I plug back in? The negative 1. So I can take that negative 1 and pull it out in front. And then I'm going to integrate 1 over u du. What is the antiderivative of 1 over u? ln, absolute value of u. And the antiderivative of du is plus c. It's just plus c. Some of us had minus c's. You don't need that there. That's where the negative came out in front. And so my final answer is negative 2, natural log. 5 minus x plus c.
Did you just change it into C?
Say again?
Did you just change it into C at the end of the problem?
It was plus c. It's always been plus c. When I take the antiderivative, it's plus c. Minus c wouldn't be counted wrong, but we just always say plus. It's a constant. I don't know if it's positive or negative. Question so far. If you look back at your bell work, we took the derivative of this thing. If you look back at your bell work, we started with that guy, and we got that guy when we took the derivative. Now we just did the antiderivative and worked backwards. Question so far? All right, let's go to the next page. So on the next page, we are getting a little bit more complicated. Here's the good news. If you are just like, I'm pretty good, we have 10 more examples of the same stuff, okay? For better or for worse. I know that's not exactly what you want to hear, but at the same time, the more practice you get with this, the better. This is the same concept over and over. It doesn't get a lot harder. If you were good so far, it'll stay the same. The only more complicated part about this is finding the u. That's the part that's the toughest thing. What am I going to make u? If you can figure that out, then everything else is pretty easy. So some suggestions. What's u going to be? The highest power of x. So if you have like an x cubed and an x squared, pick the x cubed to be your u. Natural log. If it says natural log in your problem, that's probably going to be the u. If you've got an e, it's probably going to be the exponent. The u is going to be equal to x squared. And there will be some other rules we pick up along the way, but those are the main ideas. So let's look at number 1. We are taking the antiderivative of 6 times 3x plus 2 to the 5th power. Hopefully you recognize that as a chain rule-esque problem. You've got something in the parentheses, the 3x plus 2. And so because of that, we are going to make that our u. It's got a bigger exponent. It's to the 5th power. That's the thing I'm going to start with. Find du over dx, and then find what dx is going to be. Take a second and do that. So we start off, we are finding the derivative of u. So, Devin, what's the derivative of 3x plus 2 going to get us? 3. Yep. That's du dx. I want to solve for dx. So I'm going to multiply both sides by dx. Dx is not by itself. What else do I need to do to solve for dx? Divide by 3. Divide by 3. So that's going to cancel. Everybody agree with me on that? So dx is du over 3. Let's do some substitutions. Are there any constants in this problem? Pull the 6 out in front. So it's going to be 6 integral. 3x plus 2, I'm not writing that. I'm writing u to the 5th power. Dx, I'm not writing dx because, again, I'm doing a substitution. For dx, I am writing du over 3. That's what's going in right here. So this is going to be times du over 3. Do I have any constants? The 1/3. We're going to take this 3. We're going to pull it out in front. So I'm just going to rewrite it again. What constant is now in the front? 2. 6 divided by 3 gets me 2. And then I've got u to the 5th du. After all of that work, now I finally can do the antiderivative. What's the antiderivative of u to the 5th? So u to the 5th, I'm increasing my exponent. And I'm going to multiply by the reciprocal, or I'm going to divide by my new exponent. So this is 2 times 1/6. I'm dividing by my new exponent. We increased my exponent by 1 and divided by my new exponent. And then I took the antiderivative of du, which is going to get me plus c. My final answer, 2 over 6 is 1/3. U, I don't want it to say u anymore. I'm going to plug back in what u is. U is 3x plus 2. It's really weird to say u and stuff, and I say things like u is. Like, u is smart. U is pretty. Yeah, it's weird. And then plus c. Questions so far? Thank you. Appreciate it. Let's look at example 2. The integral of the square root of 4x minus 1 all over 2. We first identify what u is. And we want to figure out what the u is going to be. Does it make sense? Again, it's the 4x minus 1 because it's complicated and because it has a weird exponent. It's being raised to the 1/2 power. That's going to be my u. Solve that problem the rest of the way. See what you can do with it. Here we go. Let u equal 4x minus 1. Spencer, what is du dx going to be here for you? 4. And so when you solve for dx, you got to multiply both sides by dx. What'd you end up getting here for dx, Spencer? 1/4 du. He had to divide by 4, so 1/4 du or du over 4. All of those work. Now that we've done that, we're going to substitute in. Do I have any constants in this integral? 1/2. I've got this 2 right there pulled out in front, so it's 1/2. The integral. U to the 1/2 power because it's square rooted. And instead of dx, I'm going to plug in what dx is, which is 1/4 du. So it's 1/4 times 1/4 du. I have another constant, so I'm going to pull that constant out in front. Now it's 1/8. Now I can finally take the antiderivative. The antiderivative of u to the 1/2 power. We increase my exponent by 1. It's 3/2. And then I divide by that exponent or multiply by the reciprocal, so it's 1/8. And it's going to be times 2/3. And it's plus c. I integrated the du. When I multiply 2/3 times 1/8, that's going to get you 1/12. I'm going to replace what u is. U is 4x minus 1. That's my answer. 1/12, 4x minus 1 to the 3/2 power plus c. Again, as you solve these things and you're like, man, that answer looks really weird, take the derivative of what you got and you'll get back to what you started with. Try 3 by yourself. Try 3 by yourself. See what you can do with it. We got to this point right here. Now I'm actually taking the antiderivative. Don't lose the fact that you have to take the antiderivative. I did all of this work, all of that work so far, besides taking that little derivative over there. This was algebra. I moved stuff in front of the integral. I didn't do any calculus. The calculus's problem is doing the integral. The integral of cosine, that guy's sine. U plus c. And then to finish this thing, I'm going to plug in what u is. 7x minus 5. That's my final answer. They look strange. There's no doubt that the process of getting to these answers is weird. You have to trust it and keep working through it until we get better and better at this. Let's try one more. Last one of the day. Example 4 is a little bit weird. Take a second with your neighbor. Identify the u. Figure out who u is. A reminder, when we're looking for u, it's the most complicated portion. The baby, the thing inside of parentheses. So it's not the x that is our u here. Our u is going to be the stuff inside the parentheses. Our u is going to be x squared plus 5. The hardest part about any of these problems is identifying u. If you can figure out who u is, what u is, then you're going to be a lot better off in life and in calculus. X squared plus 5 goes there. We're taking the derivative. Derivative of x squared plus 5. 2x. I'm going to multiply both sides by dx. So it's going to get me du over 2x is dx. These problems are tougher because when I took the derivative of this guy, I have an x in my derivative. When I get to the point that I want to take an antiderivative, there should be no more x's left in this problem. We just changed things to u, and so if we did it right, the x's should disappear. Let's see. Integral. X, I don't know what x is. I'm leaving it as x for right this second. I'm going to plug in x squared plus 5. That guy's going to be u to the 1/3 power. And then I've got dx. What can I replace dx with? Du over 2x. Here's what I'm talking about. Before we integrate, there can't be any x's left. We did a conversion. The reason we pick x squared plus 5 as my u is because when I take the derivative of it, this is going to happen. I've got an x in my denominator. I've got an x in my numerator. This is one giant fraction over here if you want it to be. This x and that x are going to cancel each other out. And so my integral is now going to look like this. I've got a 2 constant. I'm going to pull that out in front to make it 1/2. And now I just have u to the 1/3 power du. Before I integrate, there are no more x's in the problem. Finish that thing. The rest of that's easy. 1/2 u to the 4/3 x plus c. I increased My exponent made it 4/3, so then I need to divide by that exponent or multiply by the reciprocal. It's 3/8 to the 4/3 power plus c. All I have left to do is plug back in what u is, x squared plus 5. The 1/2. Remember, it was 2 on bottom with that x, so I could pull that 2 out in front. Give me a quick check